Okay. Uh, so the last time I left off with group theory, I had done till Lagrange's theorem, and now almost all of it is complete. Uh, right, and I'm not going to explain any of it because, well, first of all, there's a bit too much to explain, and secondly, it's not worth explaining. I mean, it's it's already written down and it's like pretty self-descriptive. So I don't think I need to do it in a video format. I can just send you the notes and that's enough. So in the description of this video I'll put the link for this Notion page, so if you want to check out these notes you can do that. But basically the new things that I've done, those are like I've studied normal groups to a deeper extent than what I did previously. I also studied homomorphisms, that is the properties of homomorphisms such as the kernel and the image. I mean the image is just the range, and also the three laws of isomorphism for groups, of course. Now Wikipedia has other things like for rings and who knows what, but I did it for groups. The first law uh, deals with, and also like things like quotient group and some other stuff, cosets and all that. I think quotient groups I already did, right? Yeah, I probably did that, right? But yeah, like there's a lot new stuff that I had to do. uh, I also like studied about these things called automorphisms and inner automorphisms, which are also known as conjugations, and that they have some very interesting properties, and a bunch of miscellaneous theorems that I didn't find well any use of them later on, but in the end they were kind of like nice to look at because you could prove them using some of the more core results. So the main theorems that I want to show you are these three theorems. So first you have, oh come on, why is this taking so long? Right, so first you have this theorem which says that a homomorphism going from G to H, um, right, for a given homomorphism, the function which goes from the quotient group of G with the kernel of F, where the kernel of F is basically all elements such that the homomorphism sends those elements to the identity um, of the codomain group. Well, yeah, um, right. So this capital F function, well, that goes from the quotient group of G with this kernel of F, which by the way is a group, and that's because the kernel of F is a normal group, which you can prove. I'm not going to tell you how, just you have to do it and read the notes to understand it. Right, so going from that to the image of F, which is the range basically. So this F thing, capital F thing given by capital F of X kernel of F, which is a coset of kernel of F, equal to F of small x, that's going to be an isomorphism. And like this is a very short proof, but there's a lot of build up for it. I mean, first of all, you have to like prove a bunch of smaller results to even get to the point where you can actually prove this big thing. And using this big boy, you can also prove a lot of other theorems. So the second law of isomorphism, and sorry, second theorem, it's not like Newton's laws. Okay, so the second theorem of isomorphism and the third theorem of isomorphisms, those are heavily dependent on the first theorem itself. So the second theorem says that the quotient group Hn upon n, where n is a normal group and H is just any subgroup of the big group capital G, that's isomorphic to the quotient group of H with H intersection n. And by the way, H intersection n is also normal group. So as I said, I studied normal groups in much more detail than what I did previously. The third isomorphism theorem, that is like nice. I mean, that's all I can say about it. It's like G by K by n by K. These are quotient groups, by the way. So don't think of these like as actual division. They are instead, I mean, yeah, they are kind of divisions, but basically these are quotient groups. So this big fraction like thing, that's isomorphic to G by n. So it's as if you're cancelling this 1 by K factor, but of course there's nothing like that. It's just, it looks like that, and so I like it somehow. But for this you require some some things, you require that K be a normal group of G, N be a normal group of G, and K be a subgroup of N, right? And I didn't write it as K being a normal group of N, which is a normal group of G, because K being a normal group of N is very different from K being a normal group of G, because if K is a normal group in G, well, it's automatically a normal group of any subgroup in G, but the reverse doesn't hold true. So yeah, that's the third isomorphism theorem. And yeah, I guess we can also prove this thing, and I have not put a proof for this, but yeah, at that point you'll be able to do that by yourself. Okay, so not going to explain anything, but I've basically done this group theory stuff. I'm going to move to something else. Okay, see you guys in the next video.